Okay, let's move on to the next long question. Okay, a function f of x is said to be even if f of minus x equals f of x for all x. Okay, a function is said to be odd if f of minus x equals minus f of minus x for all x. Okay, yeah, I think there's an error here. The way that I usually write the odd function is f of minus x equals minus f of x. Yeah, so that's not quite right here. You need to get rid of, what am I doing here? Yeah, you need to get rid of this minus sign. That's not right. Okay, so that's just a small typo. What symmetry does this graph y equals f of x of an even function have? Okay, right, so even functions are like cosine or x squared. In fact, any x to the power of an even number is an even function. Okay, so x squared, x to the 4, etc. And that's another reason why, if you guys have done Maclaurin or Taylor series yet, that cosine x is all of the even powers of x. So you can think of it as x to the 0 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on. So that's why cosine is a even function, and sine is an odd function for the same reason. It has all the odd numbered ones as well. So the way that you can sort of argue this is if you look at any of those curves, or if you think about this, what this transformation is. So remember that if you replace x with negative x in a function of x, that is a reflection in the y-axis. So this reflection in the y-axis, what it actually does is it does nothing to our curve. So if you reflect something in the y-axis, it must have symmetry about the line x equals 0, about the y-axis. So you could say that this has a symmetry about the y-axis, or it can be reflected about the y-axis with the mirror line of the y-axis, and it won't change. Okay, so that's the symmetry it has. The other one, though, you're saying that if you make this sort of flip, you actually get the negative of the function that you're expecting to have. And let's think about sine, what sine looks like. It has sort of a bump there, and it has that bump kind of mirrored down here. So if you reflect sine in the y-axis, then you would get your bump over here. But then you have to reflect it again in the x-axis to put it down here. Okay, to put it on top of your curve. So, so you can either say that this is sort of a symmetry where if you reflect it in the y-axis and then reflect it in the x-axis, you get your curve again. But that is actually the same as saying, let's rotate everything 180 degrees about the origin. And the way that they might like you to say this is a rotational symmetry of order 2 about the center, which is at the origin. Order 2 just means that you only need to rotate it half the circle to get back your function. Or, for instance, if you rotate it a full 360 degrees, you will get your function back kind of twice, one halfway through, the other one at the end. So you could say rotational symmetry order 2. Okay, so use these symmetries to show that the derivative of an even function is an odd function, and that the derivative of an odd function is an even function. You should not use the chain rule. Okay, so I would probably approach this by using the definition of a derivative. So let's start first with what the definition of a derivative is. So for a function f of x, f dash of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, okay, all over h. Okay, so if I can show that there's sort of a symmetry about this for even functions, then I can kind of then I can prove this. I think I'm going to end up putting like a minus sign on the outside and showing it's the sort of negative of that, and it becomes odd. So if we say, let's start with even, then we're saying that the derivative of negative of x, okay, that's the limit as h approaches 0 still of this function, but now we've replaced x with negative x, so we get negative x plus h here, and minus f of negative x here, all over h. Okay, so because it's an even function, because we're trying to prove it for even functions here, if it's an even function, the definition of an even function is that that is just f of x. Okay, and maybe we could write this a little bit differently as well. So if I write this as still the limit as h approaches 0 of, I think I'm going to write that as f of maybe minus x minus h. Okay, yeah, that looks good. And then that just becomes minus f of x. Okay, all over h. So again, here we've got a negative of something inside my function. That means that it's just the same as f of x minus h. Okay, so I'm now going to write this. I'm going to take a minus sign out so I can change the order of these two. And I'm going to write it as the limit as h approaches 0 of f of x minus f, and I'm using the fact that this function is even to get rid of that minus sign, and I don't have to put a minus on the outside, of x minus h all over h. Okay, so why does this mean that what I've really got here is negative f dash of x? Okay, why does that mean that that's what I've got there? So this would be a proof that this function is odd. Okay, this would be a proof that this function is odd, but I haven't properly explained why f of x minus f of x minus h over h is the same as our original definition of our derivative. And the reason for that is that derivatives have to be the same if you approach them from the left or from the right. So if you think about it, here what I'm doing is let's just draw a quick function or something. I'm looking at this function, I'm saying I got 2 points, x and x plus h, and I'm bringing them closer together and calculating this sort of gradient of the tangent at those 2 points, just as those points approach each other. But that should be just the same as if I use this other point here to draw my other tangent and make these 2 points approach each other. We would say this function is not differentiable at that point if those two limits approach different things. So assuming it's differentiable at the point x, then the limit approaching as h approaches 0 with the plus h should be exactly the same as the limit when we use the minus h later on. So that's why this does in fact work, and this is proving that an even function's derivative becomes an odd function. We can do the same thing for odd. I think it's very similar, this proof. So what do we do? So yeah, we can say the same thing from this line here, but then, and yes, I think you should be able to. These steps would just be slightly different, right? So f of minus x is not f of x, it is minus f of x. So that becomes a plus. And you can still factorize this here like this, but now minus x minus h is not equal to f of x minus h, it's actually equal to minus x minus h. Okay, so you don't have this negative sign on the outside, and that's it, right? So you wouldn't have that negative sign on the outside. This negative sign would kind of jump to the outside here, because that's the definition of an odd function. If you have a negative x on the inside, then that's equivalent to the function of x with the negative on the outside. It doesn't matter that it's x minus h in brackets here. It should just work the same. You could just rename this as the variable x dash, and it would still work, right? Or x prime, if you like. So that's the proof that the sort of odd function works, because you're going to end up with this limit, but without the negative sign on the outside. So you wouldn't have this negative sign here. And again, we use this argument that, if you have a differential, you approach it from either side, it's still going to equal the same thing. As long as you take that limit as h goes to 0, you're just approaching it from the left rather than the right, and if it is differentiable, those should be the same. So there's your proof that the differential of an even function is an odd function, and the differential of an odd function is an even function. Okay. I think you can also just sort of argue it using the idea of tangents and the sort of symmetry of this graph. So let's imagine that we had an even function. So let's say we had something like that. That's even, right? If I take the sort of tangent here, okay, then if I reflect that in the y-axis, I get a tangent here, and the gradient of this is in fact going to be the negative of the gradient of this one here. Okay, so you consider this by maybe taking 2 points and see how they reflect. So I don't know, this is the point x, y, and let's say this is the point, let's call it 1, 1, 1, let's call that x2, y2. Then when you reflect them, the x's are going to go negative, but the y's are going to stay the same, and then you could just use the fact that the gradient of these lines is the change in y over the change in x. So the change in y is going to be the same, I think. Actually, yeah, it's going to be the same. But the change in x is going to flip sign, so that's why it's going to be sort of the negative of it. And that's going to happen for every point on this curve. You could argue the same thing for an odd function. Or you could just say, well, it's a sort of reflection of this line, so when you reflect this line, the gradient's going to change. But if you were doing an odd function, you would have to rotate the line 180 degrees, and if you rotate any sort of straight line by 180 degrees, you get the straight line again, right? Just that if you consider it with an arrow on the end, the arrow would just sort of move all the way around to down here. But that doesn't really matter for a line; it still has the same gradient. Okay, so that's maybe a less mathematical way of arguing it, but you're going to have to write down a bit more. This is more formal, I suppose. Okay, so let's get on to the meat of this question. So we have a drawing here, okay, and they're calling A theta is the whole area here. It's not just this, that sort of isosceles triangle there. It's the isosceles triangle plus this angle theta on this sort of right angle triangle here. Okay, so let let theta be between 45 degrees and 0. Okay, that makes sense, because if theta is greater than 45 degrees, you can have a line that points around here, and then I guess it could be very large, or sort of infinite, the area, I guess. Yeah, because it's still bounded by these lines. So if it was like that, it would point on forever. So that's good to know. And if it was like this, it would be, I suppose, a lot harder to calculate what these areas are. So that makes sense, doing that, bounding it like that. Arguing geometrically, explain why a of theta plus a of minus theta equals 1/2. Okay, I can do that. So I think the half is going to come from the fact that this is a right angle triangle, the whole thing, and so that's a height of 1, and that's a base of 1. So the area of this whole right angle triangle, if I call this point A, this point B, I'd call it AOB. The triangle AOB has area 1/2, okay? And AOB, the area AOB is made up of A theta, okay? A theta plus, let's call this point here C, plus the triangle AOC. That's triangle AOC equals 1/2. Okay, but if you consider A of minus theta, that would look something like this, right? It would be a line that crosses over here. So A of minus theta would be this area here. And as y equals x is a line of symmetry on the shape, the triangle AOB, then this A of minus theta is equivalent to the triangle AOC. So this area here would be the same as the area A of minus theta. So that's actually argued it, right? You've got this triangle AOC. The triangle AOC is equal to the area of A minus theta. And you just need to say that this line y equals x is a line of symmetry. So if this angle here is minus theta, then sort of the distribution of shapes on this sort of on this side of the line y equals x is going to be the same as the sort of distribution of shapes on this side of y equals x. So that's argued it, right? I think that's pretty thorough. A of theta equals 1/2. Okay, fine. Sketch the graph of a theta. Oh, sorry. B for 0. So for theta equals 0 to 45 degrees, not inclusive. Determine a formula for A of theta. Okay, so I'm going to draw this again down here somewhere so I can label it again. So if I draw these axes again, there's 1, there's 2, and oops, sorry about that. Come on. Then there's my line. Oops. Okay, it doesn't like me to draw my lines right into the center, but it doesn't matter. Okay, so there's one line there, and here's my line y equals x here, and I also have a line that sort of comes in here. Okay, right, back to pen, back to pencil actually, and then this is theta. Okay, this is 1, this is 1. So if this meets this at 90 degrees, which it does because it's sort of a line of symmetry through there, then we can do Pythagoras to find the length here. So I think I labeled this as C, this is my A, this is my B. I'll call this M for the midpoint. So MB and M equals MO, and both of those we could say MB squared plus MO squared equals OB squared, just using Pythagoras. So that's actually equal to 1 and 2 MB squared, because MO squared is MB squared. So MB and MO are equal to 1 over root 2. Okay, that makes perfect sense. You could also think of that as 45 degrees there, and so you could use cosine 45 or sine 45, they're the same. Okay, so doing that, I now know that if MO is 1 over root 2, then CM is actually 1, CM, you could write that as 1 over root 2 times tan theta. Okay, so that's equal to CM, just because, again, this is 90 degrees, and so this length here is your opposite of that angle theta, and this here is your adjacent of that angle theta. Okay, so now I can solve this problem. So the area of the triangle OMB, okay, is just root 2 sorry, 1 over root 2 times 1 over root 2 times a half. That's just half base times height. So 1 half times 1 over root 2 times 1 over root 2. Okay, and so that is equal to 1/4. And then my other triangle, OCM, well, that's got a base of 1 over root 2 and a height of 1 over root 2 times tan theta. So doing the same thing, we get 1/4 tan theta. And the area A theta just is adding those two together. So I would write A of theta as 1/4 1 plus tan theta. Tan theta, there we are. Lovely. So that's the formula for A of theta. And I think the next thing they ask you to do is sketch it for, okay, for theta is minus 45 to 45 degrees. So tan theta, I guess I need some more lines now, axes. So let's do something like that. Sorry, it's going to cross these letters here. Back to pencil. So this is 0, this is minus 45, this is 45, this is the theta, and this is A of theta. Okay, so tan theta actually goes through the origin, right? Tan theta goes through the origin, and at 45 it would be 1, and at minus 45 it is minus 1. Okay, so if we shift that up by 1 and then multiply it all by 1/4, its new origin, its new kind of point is going to be about this quarter, and it would normally go up to 1 at 45 degrees, but now it just goes up 1/4, so at a half, and this makes perfect sense. If you think about A of theta being 45 degrees, it would cover that whole triangle. So the area should go up to a half, and it should go down to 0. And that's perfect. There we are. That's what your graph should look like, something like that. Okay, so what does it ask for now? In light of the identity in part IIA, what symmetry does the graph of A theta have? Okay, so I see, right. So, okay, so it does say in light of this A theta plus A of minus theta equals 1/2. Okay, but we can kind of see what's going on here, really. If you think about it, it's certainly going to have a symmetry of rotation of order 2 about this point 0, 1/4. So that's what I write down. It's got a rotational symmetry of order 2 about x equals 0, y equals 1/4. But how can we show that from here? We could say that, what about if we went A of theta minus 1/2 is equal to minus A of minus theta. Yeah, that shows it, right? So, actually, sorry, we'll split these into 2/4. Let's do that. Yeah, let's split them into 2/4. So if you do A of theta minus 1/4, that brings it down onto the origin, right? That would bring it here. And then all I need to say is that, yeah, this is it. So A of theta minus 1/4 is equal to minus A of minus theta minus 1/4. So if you translated it down, if you translate it down by 1/4, it'll be on the origin, and then it has this odd symmetry, right? So it has this. It's an odd function. If you A of theta minus 1/4 is an odd function, and so you've shown that here in this step. If you call this function, I don't know, A prime of theta, then you really have said that A prime of theta is minus A prime of minus theta, just with that sort of minus 1/4 included there. So that's why you have a rotational symmetry of order 2 about the point 0 1/4, because if you translate it down by a quarter in the y-axis, then you can show this odd symmetry. Okay, so without explicitly differentiating, explain why the double differential of A is equal to 0 when theta equals 0. Okay, so the differential of A, okay, so the differential of A is the same as the differential of my A prime, okay, because it's just got this extra sort of minus a quarter, and we know that constants disappear when you differentiate them, right? So that's what I would say first. So the differential of my A prime, or you can call it whatever you like, and d theta is equal to my derivative of A d theta, okay? So because A prime is we've shown that to be odd, then so A prime is odd, so the derivative is even, okay? So dA, so this whole thing is even, and so this whole thing is even, okay? And then if we differentiate an even function, we get an odd function, right? So d2a d theta squared, that whole thing has to be odd. Oh, and that's it. Okay, so and that's it, because odd functions are 0. Have a size of 0 at the origin, right? All odd functions, because when you sort of rotate them about the origin, they must pass through the origin. Otherwise, that sort of rotation would sort of change them, right? It would if they didn't pass through the origin, then their rotation would change where they sort of cross the axis. So we know that this evaluated at theta equals 0 is 0, and because of the definition of odd functions. Okay, so that sort of suits you here. Okay, so I think that finishes that question. So that question is sort of solved. I think I didn't explicitly differentiate anything, and I have explained why it equals 0. So yeah, that's question 4 solved.